Let us proceed with session 2, where we will continue solving the example that we discussed in the first session and in the process discuss the various network theorems. First, to start this question, let us start with the mesh analysis. In this case, what we do is consider a unique equation for each mesh, and for each mesh we find out what is the current flowing through it. So let's call this as I1, I2 and I3 are the three currents in the meshes, and we have to determine what are the values of these currents, and from there we can figure out then what are the voltages, A and B. I1 you can assume is 5 amperes because in that mesh there is a 5 ampere current flowing. Remember that whatever current flows out of the current source has to flow back into the current source. Okay, and the same thing applies for the other current source. So whatever current flows out of this terminal has to flow into the back into the current source. This is again due to the law of conservation. So charge cannot be created or destroyed in the circuit as it is. So whatever charge exits from one end has to re-enter from the other. So since 5 amperes has to flow into this, so you can say I1 is 5 amperes and similarly I3 is 4 amperes. Okay, so let's write that out. In this case, because we are having current sources, the mesh analysis became quite easy for us. Normally it might not be as simple. Then the only equation left to solve is due to I2, and that says that I2 minus I1 times 1 ohm plus I2 times 5 ohms plus I2 minus I3 times 2 ohms is equal to 0. What did we do here? We basically applied KVL, Kirchhoff's voltage law, because we said the sum of voltages across the loop is 0. Okay. So we said I times R1, I2 minus I1 times R1 plus I2 times R2 plus I2 minus I3 times R3. So the sum of voltages in the loop is equal to 0. So that's the equation we have written here. And if we were to solve this out, then what we can say is, so let's do this. I2, so there is a I2, there is 5 I2 and 2 I2. So 8 I2 minus I1, let me write that is equal to I1 plus 2I3. And we know what is I1 and I3. So that's equal to 5 plus 8, so 13 amperes. Okay. That implies the current I2, which was the current or IAB going from A to B, is 13 over 8. That's equal to 1.6 approximately, right? So 8 6 are 48 and 20, so about 1.62 or 1.63, 1.62 amperes. Let's put an approximate sign. So that's the current in this branch, which is flowing from A to B. Now, what are the values of VA and VB, right? VA. Well, remember, like I explained in the previous session, VA and VB by itself have no meaning. In fact, the question we should have asked is, what is VAC and what is VBC? Because C is what is connected to one end of the ammeter, or you can consider this as a common node. So we want to know what is the value of A with respect to C, or what is the value of B with respect to C. You can also find out B with respect to A, but the point is when you just say VA or VB, it doesn't mean anything. Okay, it's always potential, difference is potential with respect to some point. So if I want to find out VAC, then I would say VAC is equal to the resistance 1 ohm times the current flowing is I1 minus I2, because I1 and I2 are in opposite directions. I would have written it as I2 minus I1, but the fact is I know that I1 is 5 amperes and I2 is 1.6, so I know the current is flowing downwards, and that's going to be 5 minus 1.6 is 3.4, approximately 3.4 volts, again approximate. What about VBC? That's going to be 2 ohms times I2 minus I3. Since I've already given a direction for I2 as going in a clockwise direction and I3 going in anti-clockwise direction, so VBC should be written in this form, and that's going to be what? I2 is 1.62 and I3 is 4 amperes. So the difference between them is minus 1.4, right? I2 minus I3 is minus 1.4 approximately. So times 2 is minus 2.8. It's possible that I might be doing some of the arithmetic incorrectly, so please verify yourself. And therefore, what is the value of VAB? Is VAC plus VAC minus VBC, and that's equal to 3.4 minus of minus 2.8, so it's 6.2 volts. Okay, so that's one way of solving the circuit.